So hello everybody, welcome to the seminar. I'm very happy to introduce today's speaker, Primoz Skraba. Primoz was a member of our topology group in Ljubljana for a couple of years. Unfortunately, he deserted us and went off to London to Queen Mary University. And today he's going to give us a talk on homological percolation and persistence. So this time it won't be coffee percolated, but homology. Please, Primoz.
Thank you, Nisha, and thank you for the invitation. For this talk, it's based on some recent work with Omar Bobrovsky. The paper has been on arXiv, I think, since June. But rather than kind of just go through the paper as such and the proofs, I wanted to put things into kind of perhaps a bit wider context and how it fits in with other work with respect to persistent homology and how it fits in with how we understand persistent homology and the stability of persistent homology. So as our kind of main problem, the thing that we're going to be considering is is homological inference. So what is homological inference? Well, we have some manifold, right? And usually it's going to be, this is my bad depiction of a manifold. It's a d-dimensional manifold, and generally it'll be embedded in a higher dimensional, into a higher dimensional Euclidean space. And, well, I'll get back to exactly what that means in terms of these dimensionalities. But the way we generally consider the homological inference problem is that, right, we have some point sample, P, and from this, the problem that we consider is, can we recover the homology of the manifold, the k-dimensional homology, from this point sample, right? So this is the problem that we want to solve. And, this is a well-defined problem. There's a lot of different variations on it. But I'll kind of run through a few of the important variations and kind of what our paper says about this particular problem. Okay, so there's been a lot of work on this problem previously. Probably the most well-known bit of work on this is Niobe, Smale, Weinberger finding homology of submanifolds, where essentially this was kind of the first one that said, if we have some sample that's somehow close in kind of a probabilistic sense to the manifold, when can we recover it? And there's a lot of kind of geometry involved, and it's a very kind of, I would say, well-known paper in the field. In the same kind of probabilistic sense, there's also this paper by Adler, Bobrovsky, and Weinberger that talks about Crackle, where looks at a kind of wider range of noise models and shows that in some cases one can't really hope to do very well if the noise, if the noise of our point sample is kind of too badly behaved. On the other side, from the kind of more computational geometry side, there's this also kind of this paper, I guess quite a few years ago now, that looked at how one can do reconstruction. And this reconstruction is just really another word for homological inference in this case, but this paper used persistence to deduce this because it kind of said, well, there isn't one scale at which we can look at things that will give us the right answer, but if we look at several scales, or if we look in this case in particular 2 scales that are well chosen, we can actually recover the right answer. Kind of one other perspective I do want to mention is this kind of more statistical perspective, which was also kind of has been relatively well studied in how well one can do in terms, so there's these things called minimax rates, which essentially says how quickly one can hope to recover homology. And in kind of in the same spirit, if we kind of think about this in terms of persistence, this is kind of probably the most well-known paper, but there's been quite a bit of work on the statistics of persistence diagrams, and as things are going along, this is becoming better and better understood. And the better one understands these sorts of statistics of persistence diagrams, the better one can hope to actually apply it to this problem of homology inference. So kind of on the other side of it, we also have what I'd like to call the persistence of noise, which is what happens when there is no structure. What does that actually look like? The first person to study this was Vanessa Robbins experimentally in 2006. Then there's Matt Kale's work, Random Geometric Complexes, which kind of looked at the first, was kind of one of the first theoretical studies of this, of particularly different types of geometric complexes, specifically Čech and Rips. And then, this has been a relatively active area of research with a lot of different results on how different models behave under different assumptions. So there's much less work in terms of persistence of noise. So these are all really, I would consider these, I would count these as topology of noise, so the topology, right? So these are all rather pointwise, whereas a few years ago we looked at kind of what is the most persistent cycle one would expect to see, and we came up with some results on that. Afterwards, there's been work on limit theorems, so not just from a statistical standpoint, but more precisely for Poisson point processes, which I'll get into. Limit theorems for persistence diagrams. So again, these are just a sampling of papers. There's many more and many different results with different variants of generality and different settings and using a variety of different techniques. For someone who's interested in this generally, the place where I would send them is this very nice survey on topology of random geometric complexes, which pretty much summarizes a lot of the results that are listed here, and is fairly up to date. Okay, so this talk is about not just about homology inference, but also about persistence. So from hopefully everyone who's watching this knows what persistent homology is, and knows that persistent homology requires a space and a function, or a filtration. So essentially what we're going to look at here exclusively is the offset filtration, which is given some point sample, we grow balls around it, right? Where the parameter of the filtration is essentially the radius of the balls, right? Now, the idea here being that there's some range of radii which is going to capture the manifold correctly, right? It's going to capture the topology of the manifold correctly. Now, one quick word is I'm not really going to distinguish between the actual construction we use. So usually are we using a union of balls? Are we using the Čech complex, Delaunay-Čech alpha complex? Also we could ask Rips. We're not going to really consider these different things. We're really just going to work with the union of balls rather than any kind of simplicial structure. This just makes it a topological space, and we don't have to worry things about, are we capturing the right topology with our combinatorial structure? This is really just about the actual topological structure, the topological space. So the output of this, of course, is a persistence diagram, which is a set of points. And we're generally going to use the assumption that, in 0 dimension, because we're using the offset filtration, everything happens at 0, right? And everything is born at 0 and then just lives for some amount of time. Whereas in 1 dimension and higher dimensions, things kind of happen a little bit further later on. And, we generally consider things that are far away to be real structure and things that are near the diagonal to be noise. How the zero-dimensional diagram behaves is actually well studied in the theory of random graphs and random geometric graphs. So we're going to kind of focus on dimension 1 and up in this talk. Okay, so there's one other kind of important simplification we're going to do. It's going to be a little bit, we're not quite going to make the simplification yet, but I do want to kind of point it out in that imagine I have these two manifolds and we're going to ignore the fact rather that M is not a manifold. But these are the same points essentially, but the two underlying spaces are different. And if I look at 2 points, kind of because we're using the offset filtration, it's key that we understand the difference in distance between any 2 points. Now, one thing that we usually do, right, is that in this case, right, for almost all the points, for small enough radii, the Euclidean distance is actually very close to the intrinsic distance. So when I say d of m here, I mean the intrinsic distance to the manifold M. Whereas in this case, these 2 points have a very small Euclidean distance, but have a very large intrinsic distance. So in order to avoid this problem of is the Euclidean distance approximating the intrinsic distance, well, we're just going to assume for the most part that we have access to the intrinsic distance and that our offset is actually in the intrinsic distance. So the balls that we're growing are actually intrinsic rather than how I drew them before. Okay, so here's where we start to get into the approximation. And I do want to set things up before I get to the results in the paper, just to kind of contrast it with what in my mind is the standard approach to homology inference from a persistence perspective. So generally our go-to tool in some form is interleaving. So just to remind everyone what interleaving is, if I have 2 filtrations, 2 filtrations and I take the homology, so I get these persistence modules, and let's say that one is an offset filtration of the point sample and one is an offset of the manifold. Now, clearly, if we're intrinsic, this doesn't necessarily make sense, or rather you could think of this as just a constant, whereas this is changing until it eventually hits this, right? So until eventually these two are equal. But the point I'm trying to make here is if I have these two filtrations and they're interleaved, which is defined as having this kind of commutative diagram where if I go from one scale, I can go to the other filtration and then back, and that it commutes with just the standard filtration maps, right? So if I have this, I would say that the 2 filtrations are interleaved, and I think this is something that everyone who's listening knows, is what this means ultimately is that there's a very nice theorem that says that these 2 are, if they're epsilon interleaved filtrations, then their persistence diagrams are close. And just to remind everyone what that means very quickly, here I have 2 persistence diagrams, red points and blue points, and I try to match them up where I'm allowed to match things to the diagonal. I either match a red point to a blue point, or I match some point to the diagonal, and over all possible bijections, I try to find one that minimizes the maximum distance, right? So I think everyone knows this, and generally this kind of goes back to here, right? So this would be, let's say, the longest bar, and so any point will move at most this far under this, right? So if I put this kind of square around each blue point, I have the region that I know red points can be in. Now, what we generally think of is we think of this as noise, and we think of this as real structure. And what homology inference often does, kind of in various guises, is we say, well, we're going to set it up so that the noise and the real structure are appropriately separated. And so basically I just look at my diagram and I see things that are kind of far away. And whatever is sufficiently far away is the real structure. Okay? But how good is that? And that's really where I'm now going to get into kind of the point of the talk. Well, we know that if things are epsilon interleaved, that they're close, but how interleaved are random filtrations? So, this kind of going back to homology inference, how would we set this up? Well, let's take the case first where it is actually embedded in some Euclidean space. Well, first of all, we need to choose R small enough, and this has to do with the geometry, right? Because it's exactly this case where if I have 2 points that are too close, and if R is bigger than this, then I'm going to connect these when I really shouldn't. So R has to be small enough. And this has to do with the extrinsic geometry. So we don't really want to deal with the extrinsic geometry. We only want to deal with the intrinsic. And the other point of it is it doesn't just have to be small enough, it also has to be large enough in order so that adjacent points here are actually connected. So this is a function of how many points I have, the sampling density, and these various things, right? So even if I just have intrinsic distances, the key point is that I still have to worry that to make R large enough, right? But because it's intrinsic, once it's large enough, I have the correct topology and I don't care about anything else. So essentially, by making this assumption, I can just avoid dealing with the fact of how is it actually embedded and just worry about when does R become large enough that I can actually get the correct manifold. Okay, so there's a very well-known theorem. I don't even know what the reference would be since I think it's so well known, but this radius where things are actually covered is called the coverage radius. And it's well known that for Poisson point processes, which is kind of take a manifold and just throw points in at random uniformly with respect to the volume, R is going to have to be something like this. Right? So it's going to be log n over n to the 1 over d, where d is the dimension of the manifold. Okay? And it's important that this actually implies that there will always be a d minus 1 dimensional hole of this size, of roughly this size, right? Because before this, so before, if R is less than this, right, we don't have coverage, which means there's going to be some d minus 1 hole that's not covered. Whereas after this, it is actually covered and there's no holes because we just have the full manifold, okay? So it's not as though that, okay, after this point we're okay. It's really that we don't have the right answer before this. And in a lot of work beforehand, this was used to kind of show that we couldn't do any better, okay? So this kind of a different interpretation, kind of back to the interleaving, it really does say that the interleaving distance is exactly this, right? It can't be any smaller. So, okay, are we done here? What is the rest of this talk about? Well, the claim here is that we can do better, okay? And before I get to that, I do want to mention that there's one other phenomenon that's kind of on the way to that. And so this was work by Bobrowski and Weinberger that basically showed, kind of refined this coverage radius with respect to the dimension that we care about. So the dimension is this K here, right? And it essentially says that, first things become connected and then they become 2 connected, 3 connected, all the way up to d minus 1 connected. So we end up with isomorphisms on the underlying manifold basically in order, right? So first we get 1-dimensional homology is isomorphic, then 2-dimensional homology is isomorphic. So, first we get H1 is of our offset, right, is isomorphic to our manifold, and then H2, and then H3, and so on, right? So that's what this says. So one important thing, and this is kind of my mistake in preparing this talk, is here I actually have R, but if one looks at these papers, it's usually stated like this. And the key bit is this n times R to the d. So this is really the intensity of a Poisson point process. And basically, I'm still going to use the notation R throughout the talk because I think it's kind of a technical point, even though if one wants to be completely correct, one should really work with the intensity rather than the radius, because if you just work with the radius, it's essentially always going to be a function of n, okay? So that's just something to keep in mind, and I'll point it out as I go along. Okay, so kind of going forward to this, right, is one can kind of split up this behavior into three regimes, and this is generally what the literature does. So below this 1 over n to the 1 over d, we have the sparse regime. Then above that, we have the dense regime up to log n over n. So we don't really consider beyond this because we know we have coverage. But then at this point, this is called the thermodynamic regime. So it's important to, I drew it here as a point, but it's important to remember that this is actually I didn't write down constants. So basically, this is any constant that scales like this. So it's really kind of a very wide region. And the reason for stating it this way in 1 over n to the d is the following, is that if you look at the intensity of point processes, right, n over r to the d, in the sparse regime, it goes to 0. In the dense regime, it goes to infinity. And the thermodynamic, because it's exactly dividing by this, is that n to the r to the d is going to some constant, right? So usually people don't write it this way because it gets a little clunky, but rather just write it so that you end up with these constants, okay? So what is our theorem and what is the paper about? Well, okay, so the result essentially says that from 1 to d minus 1, right? So this is a strict inequality. So from 1 to d minus 1, the kth homology of a manifold appears in the thermodynamic regime, right? So if you think about that, that's over here somewhere, whereas coverage is only over here. So it's much, much sooner. And that's really the result I'm going to talk about today. Okay, so why should this happen, and what's so special about the thermodynamic regime? Well, it's a very well-studied thing in that, it's been studied in the 60s. There's this phenomenon called percolation. And actually, when I say percolation, I'm specifically talking about continuum percolation because this is a huge area in probability, and there's no way I could possibly do it justice. But in principle, the way to think about it is I have some random process, and I'm looking for the appearance of what's called an infinite component. So I look at the origin, and I can think I've thrown points down, and I ask, within these points, after I roll the balls around them of a given size, does there exist a path to the boundary of a box? Okay, so I've put a box around it that I call Wn, right? And now what I'm going to do is I'm going to increase the size of the box, okay? And I'm going to see, does this component still exist, right? So rather than kind of thinking of a compact manifold and throwing more points in, the alternative is that I consider a point process on the entire plane and I take a window that's increasing in size. Alternatively, I can do this scaling of the radius and just have a box and keep throwing points in. But the key notion is that what is percolation? Well, what is the infinite component is that there's such that the balls are such of a sufficient radius such that the origin is connected to the boundary as the box goes to infinity. Okay, that's kind of the key bit. Here, again, usually they do W of n in the literature, and here I use Wn and Wm, but again, there's some slightly different scalings between the compact model and this infinite model that one has to be a little bit careful of, but for the purposes of this talk, it's not kind of a critical bit. Okay, so as I said, this is a very well-studied thing. We're going to take the union of balls centered at our point sample with radius r, and we're going to look for the event that the origin is connected to infinity, and we're going to define the critical threshold the first time the probability is positive, right? So remember, this is the infimum is over the radii, or the intensities rather, as the window goes to infinity, right? So for any finite window, the probability is clearly positive, but as the window goes to infinity, is it still, does it remain positive? Is the infimum strictly positive? And that's what the critical threshold is defined as. So there is an analogous, so I clicked twice too quickly, but there's an analogous statement for the vacancy, which I'll define in a bit, which is that the origin is connected to the boundary in the complement of the union of balls. Okay? So what is a sharp threshold, which is the other kind of phenomenon we care about? It says that there exists some constant, right? So there's a constant RC, such that if you're below this critical threshold, the probability goes rapidly 0 in n, right? Whereas if you're above the critical threshold, it stays strictly positive. Now, what this means is that there almost surely exists an infinite component, right? Because we're looking at the origin, right? We can just look at many different points and we're asking, is that point connected to infinity? And because we're assuming a certain homogeneity, each point that I look at has a positive probability of being connected to infinity. So if I try enough points, almost surely I will be connected to infinity somewhere. Okay, but so this is very classical. This has been well studied since the 60s. It's still a very active area of research with many open questions. But kind of going back to homology and topology, so in the field, they primarily care about zero-dimensional things like this connected component. So as I said, we care about when homology appears. So we're going to define two events, right? So first, we're going to define E of k, and that says that this map is non-trivial, right? So there's some radius at which we go from where if I take the homology of that space, the union of balls, and map it to the manifold, this map is non-trivial. And then A of k is that this map is surjective. Okay, so this is a map that there exists, that some essential homology class of M has appeared, and this is essentially saying that all of the essential classes of M in dimension k exist. That's all that we're really saying here. Okay, so as I said, we all can also define the vacancy, which is going to become important. It's completely analogous, except that rather than taking the union of balls, you take the complement of union of balls, which is also a subspace of the manifold, and we look, is there a k cycle here? And it basically has the essential k class already appeared here. Okay, and again, the same way that all of them exist here. So this is really what we're looking for. This is the definition of what we're trying to find. Okay, so by the way, how am I doing on time? Right. Yeah. So, okay, so we rather than kind of doing the full kind of result, we need actually two different thresholds, right? So the first one says, before which we don't have any hope of, so our k of 0 is the first time 1 will appear, and this k1 is basically when the k-dimensional ones, when all of them have almost surely appeared. Okay, so kind of rather than kind of try to parse this, we can just think about it this way, that if I'm below this threshold, the probability of anything existing goes to 0, and if I'm above this threshold, everything should exist with probability 1 in the limit. Okay, so rather than a manifold, we're going to restrict ourselves to a torus, right? So a two-dimensional torus where we just are looking for these kinds of cycles, or a three-dimensional torus where these are the kind of representatives of the 3-1 cycles, and these are the representatives of the 2 cycles, or the 2 essential classes. Now, why the torus? Well, there's 2 main reasons. Number one, it has non-trivial homology in all dimensions, which means that we can expect a K-cycle, or what we call a giant K-cycle, to appear. There's different numbers of them, but that ends up being not important. And the other important bit is that we can take the flat torus. So essentially, it looks exactly like Euclidean space because we don't have to deal with curvature. Now, we don't expect curvature to really mess anything up, but it does add significant technical complications. So again, in the interest of simplifying things, we consider this flat torus. Okay, so we're dealing now with the torus. We know what we're looking for, so we're looking when these things actually will appear. Okay, so here's the theorem. And again, these constants are a little bit off, but the idea is really kind of the key point here. It's we have these two sequences, right? So that basically say that, right. So we have these two constants, all right? So we have these two sequences of constants, and below the kth one, right? Essentially, the probability that we have anything exists is exponentially decaying, and above this other one, it's approaching 1 exponentially. So again, it's exactly the same thing as before, except now we're not sure exactly how quickly it happens. There, it was really just a constant. Here we have two constants. Okay, we have kind of the lower bound and the upper bound, and below this we know nothing happens. Above it we know everything has already happened, and ideally we'd like these two things to be the same. So what can we prove? Well, in dimension 1, so in the paper that's on arXiv, we've proven this. So for dimension 1, so this is irrespective of the ambient dimension, the one-dimensional homology classes appear at the same time as this giant component. And for D-1, we have the proof, but it's not in the paper because for reasons that I'll kind of describe at the end. So, and we have this open conjecture that says that this should be the case for all k dimensions, okay? So these, the lower bound and the upper bound should agree, and they should be ordered by dimension. So this is the conjecture. In some sense, what we do know is that they are ordered by dimension, but we have this non-strict inequality, so they could in principle be all the same, but we don't really expect that to happen. Okay, so kind of just as a recap, we have these, we have one threshold for each dimension, and the top dimension is actually the coverage. So that's going off into infinity. And as we kind of throw more and more points in or consider a larger window, this transition from low probability to high probability becomes steeper and steeper. So in principle, does it become, it should kind of converge to something that's vertical in the discontinuity. And actually, how this discontinuity behaves even in even for the infinite component is not completely understood. So that's still an open question. It's known for some cases, but for some it's still open. Okay, so here's some experiments just to kind of give everyone a feeling for what these things actually look like when they appear. So here I have the 2 dimensions and 3 dimensions, and you can see it's not really this nice kind of crossing business that we would expect, but that it kind of wraps around in weird ways, right? And in 2 dimensions, it's not that bad. So here we have blue and green, and red are the edges that are shared by both. And in the in 3D, you can see it's even more convoluted, strange, and it kind of wraps around all weird places. And in 2 dimensions, and for these are the 3 essential 2 cycles when they appear, and you can see again, they're not particularly simple. They are kind of very jagged and weird, and it's not this kind of, it's not particularly nice geometrically. Okay, so kind of going to the proof outline, right? So essentially, we're going to do kind of the proof very, very, at a very high level. Basically, we're going to do sub-criticality for the occupancy and vacancy, and then use a duality theory so basically 1 and 2 are going to imply that everything has to happen in the thermodynamic regime. And then I'll talk a little bit about how sharpness is proven for first dimensional homology, and then for D-1 homology, I'll say a few words. Okay, so there's a very classical result, another very classical result from percolation literature that says that if you're subcritical, either for the occupancy or vacancy, the fact that you're actually have a very large component becomes exponentially small, right? So this makes sense because if the probability that you had a very large component was big, then it might actually extend to infinity. So in principle, all of them are kind of small, right? And this is ultimately what we really need to prove the result, because if I think about, I mean, it's kind of once you realize it, it becomes kind of obvious that if I were to have a one cycle, if I were actually to have this essential cycle, something like this, right? And let's say that it has to go through 0. Well, it has to be big, right? I mean, it has to span, it has to kind of wrap around the entire torus. So if all the components are small, then clearly this large class can't exist. And in the same way, so this is either for the occupancy or the vacancy, okay? Depending on, again, we have these two different parameters for that. Okay, now the other main ingredient of this is another kind of classical topological ingredient of Alexander duality, which connects k-dimensional homology with d-k-dimensional homology, or cohomology rather. And here's the statement. Usually, if one looks at the literature, M is usually taken as a d-dimensional sphere, but if one goes back to Hatcher, there is actually this statement for just d-dimensional manifolds. And what it says is, right, that if I have a nice enough subset of the manifold, then the kth homology of the subset is isomorphic to the d-k cohomology of this, of the complement of the manifold minus the complement, right? So why do we care about this? Well, again, we're thinking about, what we think about is this occupancy map into the torus and the vacancy map into the torus, right? So call this I, K, and I bar K. And we can use this to prove the following fact, that the Betti numbers of the torus is equal to the rank of IK plus the rank of I bar D minus K, okay? And I'll prove that in a second, but why do we care about this? Well, this is a constant, this is fixed. So essentially, if one appears in the occupancy, a D minus K cycle or class has to disappear in the vacancy, and vice versa, right? So this basically says that as soon as one appears, the other disappears, right? And we're going to use this, and this becomes kind of a key ingredient. So how do you prove this? Well, you write down part of a long exact sequence, so the vacancy into the torus, into this, and then you use Alexander duality to go back to the occupancy, and you get this kind of cohomological map. But then, because we're doing everything over fields, the rank of this map is actually the same as the rank of this map, right? So that's all there really is to it. It's a diagram chase, and one needs to set things up correctly, but afterwards it becomes relatively obvious. So this actually does buy us a lot already, because what it says is, well, here I have no, essentially what this says is I have no one-dimensional homology, and actually I don't have any homology in the occupancy, which means I have all homology in the vacancy. And here, because I don't have anything in the vacancy, right? I don't have any homology in the vacancy above dimension 0, then I have everything in the occupancy. And this is basically the proof of the statement that I had, right? Essentially, everything has to happen inside here because, well, I mean, there's one other ingredient that these things are ordered, but that's not terribly difficult. But because you don't have one-dimensional homology below this, in the occupancy, you have to have everything in the vacancy, and vice versa. So just with these two results, we can observe that everything has to happen in the thermodynamic regime. Now, the other ingredient for this is sharpness, right? So we don't want just to say that the things exist in this threshold, but at least for dimension 1, we would want to show that as soon as we're above this threshold, that we actually do have a non-trivial one cycle, okay? So the way to think about this is, well, there's no reason a priori why this should be the case. So first of all, we could have an infinite component that just goes off in one direction. Now, that's very unlikely for kind of various probabilistic reasons. So one could say, okay, well, if I'm connected to this side, I'm also connected to this side. But there's another problem, right? I don't need just there to be this crossing. So this is usually something that in probability is studied as crossings. But, let's say I forget about the origin, but I just have this crossing. But, that's not enough, right? Because I need these 2 points to actually link up together in order to form a one cycle. I mean, as I've drawn it here, it's not actually a one cycle. So I need to prove that these two will actually link up somehow. And the key idea in the proof is that we have all the other components other than this crossing one are small. Okay, and so there's a statement of a theorem from Penrose that basically says exactly this for the occupancy that's cited in our paper, and it essentially says that the second largest component is much smaller, is kind of exponentially decaying versus the largest one. So how do we use this? Well, we just kind of cover our torus with different blocks, right? So I have these three blocks, right? And R1, R2, and R3. And again, R3 kind of wraps around this. The bottom one is the same as the top one, right? So I've just kind of repeated it. And essentially what I'm going to say is I'm going to build my non-trivial cycle using the results that we know. So we know that we have these crossing components because we're above the threshold. That we know. And we know that all the second largest components are smaller. So essentially one takes the crossing component from, let's say, R2, right? So we have this one. And there's a crossing component for R1. Now, when I restrict, right, if both of these were crossing components, well, then I would have two disjoint large components because I set it up so that even these slabs are somehow large. But because of the theorem, I know, because of Penrose's result, I know that these can't actually happen, so I can infer that this one is connected. And I just repeat the argument 3 times, and so I have this component, and I know it's connected to this component, and then the red one, right, is kind of up here. I know that this one is connected to this, and I know the green is connected to the blue. Right? Again, and it's the same argument over and over again, in just that when I do the restriction, these 2 large components have to restrict to one another, because the second largest one is just too small, and you can't restrict something that's very big to something that's really small and not crossing. Okay, there's a few subtleties here that one needs to take care of, but ultimately that's really the key idea in the proof. Okay, so this idea is very simple. It basically relies almost completely on previously known results. But what about the vacancy, right? So for the D-1, we also expect that there's a sharp threshold, and we basically need the same result, right? That the second largest component is small. Now this is actually turns out to be quite involved. Which is why it's not in the paper. And the short answer of why this happens is that the geometry is much more complicated for the vacancy. So here I have my union of balls, right? And if I look at the vacancy, right, it's in some sense much trickier. And specifically, the key problem is if I think about this ball, it has some minimum volume, whereas things like this, the volume of the vacancy is not really very well controlled. In the same way, if I think about having disjoint clusters in the occupancy, I can't have too many, right? Because there's some sort of packing bound that goes on in how many disjoint balls I can have around a point. Whereas for the vacancy, I can set it up so that I can have an arbitrary number of disjoint components in the vacancy in an arbitrarily small area. So that's kind of the first problem. And then the second kind of technical problem has to do very much with probability and Poisson point processes, in that in this, for any kind of window, you're only really allowed to consider points within the window. So what could happen is you have this crossing that gets killed by points that are outside of the window. And for the occupancy, again, this isn't a problem, because if you're connected in the occupancy, any points you consider outside just make it bigger, make the component bigger. They can't make it smaller. Whereas here it makes it smaller, which then kind of complicates kind of the analysis. And again, this is 10 pages of proofs that one needs to do in order to kind of sort out all of these things. Right. Okay, so in summation, and kind of I'm just going to say a few more words about this, is that we saw that the interleaving distance is log n over n, but really that most of the global structure that we expect to see appears much, much sooner, right? There's this log factor that both of these are going to 0 in the compact case, but this one goes to 0 much, much faster. And even though, interleaving, I would say, is, the way I think of kind of how we do things in persistence, and even though this isn't particularly useful for this problem, this persistence-like approach is still useful. This is how we manage to define what higher dimensional percolation looks like. Duality ends up being very important. And also, I didn't mention this, but for the vacancy, kind of a very clever way of dealing with these problems of complicated geometry is if we consider kind of a persistence-like approach where we consider 2 radii, right, and we thicken things a little bit, well, then we end up with lower bounds on volumes and kind of nicer geometry. The persistence-like idea allows us to simplify the geometry quite a bit. So I think persistence-like approaches are still very useful. I think kind of the more interesting question is, interleaving distance is a very classical, and it's a very categorical type of construction, and it makes sense in the way that it's done. But for these kinds of random complexes and this kind of random topology, is there an alternative notion of interleaving that might make sense? So here I don't really have an answer. The only thing that I will kind of point to is this other paper with Catherine Turner, where we looked at Wasserstein distance for persistence diagrams. And there, again, interleaving distance is just too coarse a measure, and one needs to define kind of a finer notion of interleaving. So I think this is just generally an interesting question that I'm asking rather than kind of really suggesting an answer. One other kind of bit that I want to kind of bring it back to the beginning of the talk, where we had about stability and homological inference. If one thinks about what the results ultimately say, is that anything that's kind of sufficiently high up here, so I know we did everything on the torus, but in principle this can be generalized and, subject to time, will be written up hopefully by the end of the year, hopefully by, certainly hopefully by the spring. But one can kind of say any structure that's big enough is going to follow this percolation. This is going to have this kind of percolation behavior, which means that everything kind of sufficiently up here, right, is going to be stable, and immensely stable if the conjecture is true, right? It's going to really converge to a point very, very quickly. Whereas down here where we have noise, right, so this would be kind of the very stable region because these are global structures. And down here where we have noise, we're beginning to understand, the various limit theorems. I mean, I gave some of the results, but, noise tends to converge to some sort of limit very quickly as well. So in some sense, the point I'm trying to get across is that, while interleaving is a very, the classical stability results tells us a lot, in truth, it looks as though persistence diagrams are actually much, much more stable than we would have previously expected. So with that, kind of the takeaway that I hope that you got from this is that, interleaving, even though it's kind of our go-to tool in persistence, it is a very coarse bound in a lot of cases. The other point that I hopefully is that, percolation is intrinsically a topological phenomena, and it's very interesting topologically, and I think there's a lot of interesting questions here. And the last part is just what I said, is that it seems as though global structures are immensely stable, just due to kind of probabilistic effects rather than topological. So I think that's certainly kind of a very interesting direction for future research. Kind of on the flip side, one can also ask, all these probabilistic tools that people have defined, how can we understand them topologically? The last part, then the thing that I'll really conclude with, is that there's really many interesting and difficult open questions at the intersection of topology and probability. And it really is kind of, the survey is a great place to start, but there are a lot of different results and a lot of different techniques are being developed and incorporated, and it really is kind of an exciting place to be. With that, I'll also kind of just quickly point out some of the percolation literature we use. There's a lot more, but the percolation literature is certainly something that I think applied topology should look at more closely. And with that, I'll conclude, and thank you.
Well, thank you very much, Primoz, for your really interesting talk. So do we have any questions?
Yes. One question. Do you think that something new happens for twisted torus instead of just torus?
I mean, in principle, no, right? Because the whole way, the way that percolation is in some sense set up is that it is a global phenomenon, but if one looks at the proofs, it's a fundamentally probabilistic appearance. So it's going to be kind of defined, it's going to be a kind of a consequence of purely local phenomena. So, I said, for any kind of manifold, again, we don't have this kind of written down precisely, but you could think about, rather than the torus, that I will take any loop, right? And essentially, I will build my cover in a sufficiently nice way around that loop. And, because I just look at this as maybe like some sort of submanifold, I will be able to approximate it, right? So, this all comes with caveats of that it's, number one, not written down. And if there's one thing that we've learned is that for these types of things, the devil really is in the details. And two, I'm presupposing that the homology class that one wants to capture is representable as a submanifold, which obviously is not always true. But assuming those two things are the same, one would expect kind of exactly the same threshold in the limit.
Great, thank you.
Any more questions? I was wondering, you talked about this other approach to measuring distances instead of the interleaving. So do you have
Right.
any ideas how to attack this?
For the Wasserstein distance, this showed up in the sense that we wanted to, that, one wants to not just look at does the diagram commute, but one wants to measure how much of the diagram commutes, right? So if I think about this as interleaving, one could say that, let's say I know that my limit has, let's say I'm in the 2 torus, so I have 2 one-dimensional cycles. What I'm really saying is that if I go from one filtration to the other and back, the kind of pullback in some sense, or the image of the pullback into the space, or some sort of persistent notion will be at least of dimension 2, right? So in some sense, one needs a slightly more refined thing of not just everything or nothing, but some more quantitative measure of these things. There's, again, this becomes very kind of fiddly and problematic in the way we did in Wasserstein is to basically, in the Wasserstein paper, was to introduce the notion of an interleaving object, which is essentially some object that has maps to both of the filtrations that you're trying to approximate, and somehow that captures the phenomena that we want. That enabled us to kind of capture this phenomena of counting different things differently. But I still think that there is this kind of, quantitative interleaving that one can write down. I have tried to write it down. One can write down something reasonable, but I certainly haven't convinced myself that I know what the right answer is. In some sense, you want to kind of say, okay, at this epsilon, I have this much of the diagram commuting, right? This kind of rank commutes, and then I increase it, and maybe, the rank increases, and so I take some difference and I somehow integrate over to get the distance. It's much more complicated and less categorical, but the upshot is that you do get this kind of more, much sharper analytic results for your trouble.
So this Wasserstein approach would be like more geometric, and then it might help you come up with strictly this algebraic.
It doesn't necessarily. So kind of the other part that I forgot to mention is the interesting thing is, we have Wasserstein stability, but Wasserstein stability doesn't say anything about very persistent cycles, right? Things that are very persistent cycles are just one point, so you can move them around a lot. But it just says that the mass as a whole isn't changing very much. But if I combine the two results, I have that the Wasserstein stability, that the mass isn't changing much, but the points that are far from the diagonal actually aren't moving very much at all. In fact, they're converging to a point. And I think that's fundamentally interesting.
Thanks. Any more questions? Well, in that case, I'd like to thank you very much for the talk. I thought it was really, really great for me. It opened up a totally new field. So thanks. Very interesting.
And have a nice weekend, everyone.
Yes, thank you very much.